Alright folks, in this video we're going to talk about oxidation reduction reactions. This is going to be the last video of the third topic in chapter 8. Let's take a look at these two examples. Well, in chemistry, electron won't be transferred in a lot of chemical reactions, okay? But there are many reactions in which electron will be transferred from one atom to another atom or one element to another element, okay? So if you have electron transferring involved in a chemical reaction, that reaction will be oxidation reduction reaction. Let's take a look at these two examples. Top one is between hydrogen gas and oxygen gas. Product is water. In this reaction, electron will be transferred from hydrogen to oxygen to form the product. Okay, so this is going to be oxidation reduction reaction. Second example, between sodium solid and the chlorine gas. Okay, product sodium chloride. And in this reaction, electron will be transferred from sodium to chlorine. Okay. Again, since electron transferring is involved, this is going to be an oxidation reduction reaction. Alright, so in this video, we're going to talk about how we identify whether a reaction is oxidation reduction reaction, and also how we identify reductants and oxidants. Okay. Before we do that, we need to talk about oxidation states. And oxidation states sometimes is also called oxidation numbers. Okay. How do we define oxidation states? Well, let's talk about the oxidation state for ions or the covalent compound, okay, or the atoms in the covalent compound. Or for ions, the oxidation state would be the charge of an ion, okay. But for an atom in a covalent compound, then the oxidation state would be the charge. Remember the quote sign here? The charge here is not the charge here in the ion. Okay, so we'll talk about the examples in a moment. But for an atom in a covalent compound, then the oxidation state would be the charge of an atom if all shared electrons were assigned to the atom with higher electron negativity. Okay, so the En represents electron negativity. All right, now let's take a look at it. Might sounds very confusing. Let's take a look at the specific example. First example, let's see copper chloride. Well, we know that copper chloride is an ionic compound. Okay, copper 2 plus would be the cation, and chloride would be the anion. Of course, you need two chloride anions to balance the two positive charges of each copper cation. Okay. Now, how do we assign oxidation states for both ions? According to the definition here, the ions, the oxidation state of the ion would be the charge of the ion itself. Therefore, for copper 2 plus, the oxidation state would be positive 2. For chloride, since the charge is 1 minus, we didn't show you 1 there, but you should know that this is 1 minus. Okay, so the oxidation state would be negative 1. I do want to remind you about one thing. When we label a charge, we write number first and sign followed. Okay, like 2 plus and 1 minus. But when we write oxidation state, we write sign first and number followed. Okay, and so this is the ions. Now, how about atoms in a covalent compound? Let's take a look at the hydrogen chloride. Well, hydrogen chloride, we know that they will share one pair. Okay, I'll use a different color. Okay, so the red one is from hydrogen. Okay, if you wanted me to write the full Lewis structure here, you would have 3 more lone pairs on chlorine. Okay, so well, here the red electron comes from hydrogen, the black electron comes from chlorine. Well, and we know that this is a covalent bond, and the two electrons are shared by hydrogen and chlorine. Chlorine has higher electron negativity than hydrogen, so most of the time those two electrons will move around chlorine instead of hydrogen. Okay, so that's what we learned before when we discussed the electron negativity. But how do we assign the oxidation states for hydrogen and chlorine? Well, in this case, we have to do some assumptions. Okay, so for let's focus on chlorine. So for chlorine, it will be the charge of the chlorine if all of the two electrons were assigned to the chlorine, which has a higher electron negativity than hydrogen. Okay, what does that mean? Well, we know that for chlorine, it has 7 valence electrons. If the chlorine got both shared electrons, then it sounds like it gets one more electron to reach the octets. Okay, so since it gets electron, okay, we should have a quote sign on the gets. Well, since it gets 2 electrons here, gets both shared electrons, it gains one more electron than its valence electrons. Therefore, it's going to be labeled as -1 as oxidation state. Okay, so it's sort of like hydrogen will lose 1 electron to chlorine, so chlorine will label it as -1. But for hydrogen, in this case, since it's losing 1 electron, so it's going to be labeled as +1 as the oxidation state. Okay, so that's what the assumption here, if for it means for this atoms involved in a covalent bond. Okay, let's see another example. Oxygen, it has 2 lone pairs, and we know it. And here, this is 2 more electrons from oxygen. Now, from hydrogen, and we know that it will share. Each hydrogen will share 1 electron. Will share 2 electrons with oxygen. Okay. Now, again, based on the description here, we can assume that oxygen will get 2 electrons from both hydrogens to reach octet rule. Okay, since it gets 2 electrons, then we label that as -2. Okay, if you write the formula of water, so we label the -2 on top of the oxygen. And for hydrogen, since it loses 1 electron, let's assume that, like we said here, we assume that both electrons belongs to oxygen only. So sounds like hydrogen lose 1 electron to oxygen. Therefore, we label the oxidation state of hydrogen as +1. All right, let's see one more example. Carbon dioxide, okay, CO2. Well, we know CO2, it has 2 double bonds on the 2 sides of carbon dioxide. Okay, here we know, let me write it here. Okay, all right, and I would like to, again, like we did for these 2 examples, I would like to get the electrons for each double bond, so that I use the black dots to represent the electrons from carbon, and for oxygen, let me use like blue color. Okay, so blue dots. Oops, this one should have just 2 lone pairs. Oops. Okay, so okay, now let's take a look at this structure. Well, according to the description here, we will assume that those 4 electrons belongs to oxygen only, since oxygen has higher electron negativity. So before the formation of the carbon oxygen double bond, oxygen has 6 electrons. Now, if all 4 shared electrons belong to oxygen, that means oxygen will get 2 more electrons. Therefore, we'll label the oxidation state for oxygen as -2. And same thing for this oxygen. This oxygen will get 2 more electrons to satisfy octet rule. Therefore, it's going to be -2. For carbon, in this case, okay, we'll assume that it will lose 2 electrons to each carbon, to each oxygen. Therefore, carbon will lose total 4 electrons. Okay, so that's going to be +4. All right, so if you want to label the charge, if you want to label the oxidation state on the formula, carbon +4, oxygen -2. Well, one thing I want to remind you is when we label the oxidation state, we are talking about the oxidation state of one atom. Okay, a common mistake, I'll write it here, is okay, +4, but you label that as -4 on top of oxygen. This is not correct. Okay, well, I know that's a common misunderstanding. Is it sounds like that we need to multiply -2 with +2 to get -4, but that's not the case. When we talk about oxidation state, we are talking about an oxidation state of one atom, okay, not a group of atoms. All right, so I want you to pay enough attention to that. All right. Here, this slide shows us some general rules or general guidelines for us to follow when we try to figure out the oxidation state. Well, here, let's take a look at them one by one. Okay, I would like to. Okay, first one, each atom in free element has an oxidation state of 0. Well, like a zinc, oxygen gas, iodide gas, P4, the phosphorus element, and sulfur 8. If it has only one element in the formula, it's not going to talk about, we're not going to talk about the electron transferring, right? So the oxidation state of all of them will be 0. No electron transferring process, okay? Now, second, rule number 2, in simple ions, oxidation state equals to the charge on ion. Well, we know this already based on the discussion on the previous slide. For instance, lithium plus, well, the oxidation state of lithium would be +1, okay? Iron 3 plus, then oxidation state would be +3. Well, for sulfur S2 minus, since the charge is 2 minus, so for each one of them, okay, so for sulfur, it's going to be -2, iron +3, and the lithium +1. Okay, so this is rule number 2. The rule number 3, oxide usually has an oxidation state of -2. Like water, we talked about that in a moment ago. Okay, -2 in this case. And sodium oxide, -2, right? And okay, let's see, calcium oxide, -2. Okay, so whenever you have oxygen in the formula, most likely it would be -2. There are some exceptions. For instance, peroxide. Remember, peroxide, hydrogen peroxide is a very common household chemical. Okay, we use them to, as the cleaning reagent to clean the wounds, for instance. Okay, for this case, oxygen would be -1. Okay, but this is not required. All right, I just need you to know for oxygen oxide, oxidation state would be -2. Hydrogen or proton, hydrogen cation, always +1. Okay, so for water here, it's going to be +1. Okay, and hydrogen sulfide, that's going to be +1. Hydrochloric acid, +1 or +1. Okay, sorry if I said the -1. It should be +1. Okay, all right, these are the hydrogens and oxide. Now, rule number 4, fluoride always -1. Okay, fluoride has the highest in electron negativity across the periodic table. It always get one more electron from other species to reach this octet. Therefore, for fluoride, always -1, like sodium fluoride, -1, +1 for sodium. Okay, hydrofluoric acid, -1 for fluoride, +1 for hydrogen. Okay, so this is fluoride. Other halogens usually are -1, like we talked about here, hydrochloric acid, um, negative ne -1 for chloride, and sodium chloride, -1 for chloride, and potassium bromide, okay, -1 oxidation state for bromide. Well, lithium iodide, -1. Okay, so these are the, but this is there are a lot of exceptions for other halogens like bromide and chloride and iodides. We will do some practicing about this about this unusual oxidation state involving halogens. Okay, but most of the time they're going to be -1. Rule number 5: Group 1A metal always +1. Group 2A metal always +2. Well, we know that we talked about sodium oxide. Okay, so +1, sodium group 1 metal, and sodium chloride +1, and okay, sodium fluoride +1, calcium group 2 elements +2. Okay, it's because group 1A metal, they always lose 1 electron to satisfy octet rule. For group 2 metals, they always lose 2 electrons to satisfy octet rule. Okay, so that's why we can assign the +1 for group 1A metal cations and +2 for group 2A metal cations. Now the next one is the a little bit of calculation. The sum of oxidation state for a neutral compound would be 0. For an ion, it's going to be equals to the overall charge. What do I mean by that? Let's see. How about carbon dioxide? Okay, carbon dioxide is a neutral molecule. All right. So, and based on the rule number 3, oxide -2. Okay, so we can label -2 on top of oxide. But if you want to calculate how much the oxidation state of carbon has, then you can do a simple calculation. Okay, I label question mark for the oxidation state of carbon. According to the first part of the step, the rule number 6, this is a neutral molecule. So the sum of the oxidation state of carbon dioxide should be 0. Okay, so that means question mark plus -2 times 2. Okay, this -2 is the oxidation state of 1 oxide. This 2 is the 2 oxide in carbon dioxide. So this one should be equals to 0. And if you do the math, it will tell you that question mark equals to +4. So that's why we label carbon dioxide oxygen -2 and carbon +4. Okay, oxidation state. Now, how about the second part of rule number 6, overall charge for an ion? Well, let's just take a look at the nitrate, NO3 minus. Well, this is a polyatomic ion. Well, between nitrogen and oxygen, apparently oxygen is easier to identify its oxidation state because it's oxide -2. Okay, so I want to calculate how much the oxidation state of nitrogen is. Oxide -2. All right, again, according to the second part of rule number 6, the question mark plus -2 times 3 equals to -1 overall charge of the ion. -2, oxidation state of oxide. 3, because you have 3 oxide, and the -1 is the charge. Okay, so now by setting up such an equation, we can calculate the question mark, which is the oxidation state of nitrogen. That's going to be +5. Okay, so NO3 minus oxidation state for oxide, -2, oxidation state for nitrogen, going to be +5. Okay, so these are the general rules that we want to follow. All right, so this is the part 1 of oxidation reduction reactions video, and we'll have a second part for this topic.